Sample problem number 1. A 600 pounds per feet uniformly distributed load is applied to the left half of the cantilever beam ABC as shown in the figure. Determine the magnitude of the force P that must be applied as shown so that the displacement at A is 0. So we are given here with our figure wherein we're going to identify the magnitude of our force P. So our force P is unknown. So for this one, we are given with the load diagram. This is our load diagram. We are also given with our bending moment diagram. So from this bending moment diagram, we can compute now for the value for our magnitude of P. So for this one, since this is P for our for our bending moment diagram, so that is P, since this will be our reference point. So we choose point C as our fixed support. So this will be our reference point so that we can draw our bending moment diagram. Since at point C is our reference point, this is our fixed support, this is our reference point. So for our bending moment diagram, we start with our P, concentrated load. So P times the distance from point A towards point C, which is our reference point. So this will be 8P. Since this is a concentrated load, so you will have your triangular loading. Then we have 600 pounds per feet. This is a uniformly distributed. So this will be downward. So that will be 600 times the length of this, which is 4. So 600 times 4. Then the distance from the centroid towards our reference point, which is point C, so that is times 6. So we have 600 times 4 times 6, so we get here 4,400. So that is negative 4,400. So this will be a curve. You will have a curvature at this point. So that will be negative 4,800. Now we have drawn our bending moment diagram. We only have two loads on our load diagram. So that we can compute for our P. To compute for our P, we just have to sum up our areas of our bending moment diagram. Then for this one, we can resolve this by having subdividing our figure into different shapes because it contains, so we can have here so this one, we have 4 figures. We have it rectangle, triangle, and a parabola for this. For this our figure. So for this one, to subdivide, so we can have this. It was divided into 4. We have one triangle, one rectangle, and 2 parabolas. So from this portion, we subdivide. From this portion, this will be, if we're going to get the value, the intensity here, so that will be 600 times 4 times 2. So from the centroid towards point B, so that will be times 2. So that will be 600 times the length, which is 4, times from the centroid towards point B is 2. So we get 4,800. So that is negative 4,800. So we have now the intensity at this point. So you can draw here a line, a broken line, and this portion will have a rectangular shape. So now, afterwards, you have to determine the distance from the centroid towards point A. So for this one, we have to take note. We chose our from the bending moment diagram, we choose point A as our reference point. So because we're going to have the tangential deviation at point A with respect to C. So the tangential deviation at point A with respect to C, So meaning to say this will be our reference point. So that will be getting the value of the distance from the centroid towards point A. So we simply have to, for of course, for a rectangle that is from that point towards this point, that is 1/3, 2/3, so 2/3 of the length. Then if that is a parabola, from that portion, from this portion towards that portion, that is 3/4 of the length. So we have now identified 16/3. We have this one as 3 because that is 3/4 of 4. So cancel out 4. So you got 3 for this one. This is from the center, that is 2. Then plus, you still have this distance plus 4. So you got 6. This one, you have 4/3 of 4 and 4/3 of 4, and you have plus 4. So we have here 20/3. Then afterwards, we have to take note that from our sketch, from the elastic curve sketch, we have here the tangent at C. So you have to take note that for this one, this is a for the boundary conditions, based on the boundary condition, this is a cantilever at point C. So meaning to say at point C, our displacement is equal to 0, and our theta also at point C is equal to 0. Then at point A, the displacement also at point A is equal to 0. So that will be our, at point A, the displacement is also equal to 0. So for this one, since uh, slope, the slope which is represented by this theta c is equal to 0, so meaning to say the slope, the elastic curve, the slope of the elastic curve at point C is 0. So meaning to say our tangential deviation of A, the tangential deviation of A with respect to C is equal to 0. So which means that from our formula, based on our formula, that the tangential deviation of A with respect to C, the formula is equal to this form, which is area of the moment over EI diagram from between A to C times our bar x at point A is equal to 0. So meaning to times our bar x at point A. So meaning to say our reference point from the centroid is at point A. So since our slope at point A is, at point C rather, since the slope at point C is equal to 0, so meaning to say the tangential deviation of point A with respect to C is equal to 0. So therefore, using this equation, equating that to 0, so since this is equal to 0, so equal to the area of the moment diagram. So we simply have to get the area of this bending moment diagram. You sum up all the areas of this figure. So you can have now you start with the triangle, so area of the triangle, then minus, you have the rectangle, then you have this parabola and another parabola. So therefore, we can have, and that is equal to 0 since the tangential deviation at point A is equal to 0. So equate that to 0. So therefore, we have only one unknown, which is our P. This is our unknown, which is our P. So if we try to simplify, you get the value, which is 1,537.5 pounds. The second problem is, the simply supported beam as shown in the figure supports a concentrated load of 300 Newton as shown. Using EI, which is 20.48 times 10 to the third Newton meter squared, determine letter A, the slope angle of the elastic curve at point A. Letter B, number 2, the displacement at point D. Okay, we're going to choose our fixed support. So based on our figure, we're going to use as fixed support at point C. So using point C as our fixed support, so meaning to say this will be our reference point as we draw our bending moment diagram. So as we draw our bending moment diagram, so we're going to start with, we're going to have our bending moment diagram. So we start with our concentrated load, which is 100 multiplied to our length, which is 2 plus 1 towards point C. So since this is a concentrated load, so you're going to have a triangle. So we have now our triangle. So this is now 300 Newton. So we have a concentrated load at point B, which is 300 downward. So 300 times 1, that is the distance from point B towards point C. So this is also 300. So that is negative 300. Now we have our bending moment diagram. Let us try to draw our elastic curve. So if we try to draw our elastic curve from point A towards point C. So let us try to draw our elastic curve that is from point A towards point C. So we have here our elastic curve. So this is point E, you have point C. Then we draw a line, draw a tangent line at point A. So therefore, this is our tangential deviation of point C with respect to A. And we're going to identify the displacement at point D. So this is point D. So this will be the displacement at point D. So this one, this is our, at this point, at point D, this is our tangential deviation at point D with respect to A. So therefore, based on our illustration, we can identify our, for the first part, we're going to solve for the slope angle of the elastic curve at point A. So to identify the slope angle at point A, we're going to use our tangential deviation at points of point C with respect to A. So we have here, so the first one is the slope angle of the elastic curve at point A. So we're going to have tangential deviation of point C with respect to A, that is equivalent to the area of the moment diagram all over EI, then that is from point A to point C multiplied to bar X relative to point C. Therefore, this is equivalent to 1 over EI the value is 20.48 times 10 to the third multiplied to the areas of our bending moment diagram. So we have 1/2 times 300 times 3 times moment arm distance 1/3 towards point C. Then minus 1/2 times 300 times 1 times the moment arm distance towards point C. And if you try to simplify, we have the value which is equivalent to the value here as we try to simplify 0.019531 meters.